Okay, very good. Finally here, finally ready. 15 minutes late. So we have this series on the pearls of computation, and we've particularly been looking at the big names, the big prizes, particularly the Turing Award. And it's appropriate that we look at this year's Turing Award. I'd say, formally speaking, it's a 2013 Turing Award, but it was awarded this year. So the March 18, they sent out a note. ACM today named Leslie Lamport as the recipient of the 2013 Turing Award for imposing clear, well-defined coherence on the seemingly chaotic behavior of distributed computing systems, and so on. These contributions have resulted in improved correctness, performance, and reliability of computer systems. And I wanted to talk a little bit about what he has done and try to dig into a little bit what got him actually to do that, what brought him there, and try to get some sense of what does this really mean, what's the point of it. Now, he's accomplished quite a bit, and actually getting into any one of them would take more than one talk, so it will be quite superficial. It might give you some ideas. Well, he was born in 1941. He went to school in Bronx High School and got a summer job, got to work with a computer, actually, not very usual at the time. And there was an interesting quote from that. Somebody was commenting, he's playing with it just like it's a toy. He thought, well, it's all right. It was a wonderful toy, and these grown-ups didn't appreciate what a wonderful toy it was. I've never done interesting research by sitting down and deciding that X is a very interesting problem, and therefore I should solve X. I doubt if anyone else has either. Good research comes from thinking that something is fun and playing with it. Well, he then went to MIT, presumably to study engineering, but quickly decided it was not for him. It didn't seem appealing at all. Instead, he went into mathematics, but then found that math was in a horrible state at the time. Basically, you didn't want to get dirty by all this applied stuff, and that permeated the thinking. And basically, the idea was that if you could just make it somehow more abstract, more opaque, then that would be great because you got further away from the grotty reality. So he finished the degree and actually enrolled for a Ph.D. at the nearby Brandeis, but then gave up during the second year, partly because he thought that math was pointless because it's so far removed from reality. So for a while he was thinking of taking up a music career, maybe studied music and composition. But he actually wound up taking a teaching position at a small liberal arts college in Vermont. And then he got his first experience at trying to teach people to prove. I tried to teach my students how to write a proof, but I failed. I realize now that the reason I was unsuccessful was that I was under the delusion that there should be a rigorous and precise way mathematical proofs are written, when in fact mathematical proofs are a literary form and aren't really rigorous. That's something I'm interested in changing. This has actually affected his style from then on. He's been unusually strong advocator or more formal, more rigorous style. I'm careful proofs. Well, he did go back to school, and while he was in grad school, he worked part-time for a computer company called the Massachusetts Computer Associates, or COMPAS for short. And their job, they had a task of writing a Fortran compiler for this computer, ILIAC 4, which was actually top of the line at the time. It had actually 64 processors to solve a massively numerical computations. And the task was then therefore to take sequential programs, then compile it to do multiple instructions at the time. So this is pretty advanced and basically an early introduction into concurrency, concurrent computing. Now, a few years later, he shifted. He joined a company called research laboratory called SIR International, which it was an offshoot from Stanford. Used to be called Stanford Research or something such. And they got a project from NASA to try to design computers to help control airplanes. And the task was to really figure out how can we make them reliable enough for the task. Well, this was a part of this, what was called the SIFT project, that's SRI. It was an experimental study, but actually it was successful enough to turn into a successful product used widely in safety critical fields such as nuclear industry and oil production. So the name actually stands for Software Implemented Fault Tolerance. It's a flight control system that is a control an airplane, and the objective was really to get around hardware failures. Hardware usually works, but it eventually fails. And you don't want it to fail while you're flying the plane. That's basically the point. If you are working analog, then you have basically more workarounds for the pilot to do something clever. But once you have a computer there, there's not much he can do. So the idea is to reduce the hardware failure by implementing as much of the system as possible in software. Interesting idea. The basic principle is to use replication. Namely, you have multiple copies of each machine. And the machine has the processor, it has its own memory, it has its own clock even the separate buses. And then you have those machines actually do voting on what are their decisions on the task at the hand. So even if one of them fails, okay, the other ones can come to the right decision. Now, for this purpose, the synchronization is really fundamental. They have different clocks, as I mentioned, so you need to be concerned about that. So this brings us to fault tolerance. We usually deal with just single computers. We assume that they work, but once we expect faults, we know that, well, a single computer is not enough, so you need at least two. But is two enough? Well, what if they fail unpredictably? If it just gives up, then it's okay, the other one can take over. But what if it doesn't want to allow it to be taken over? Who's going to be in control? Well, then you need three, right? And so you just take majority vote, or they take the median of the values. But their insight actually was, is that actually enough? Let's think about this a little bit. Let's think about clock synchronizations. You have these three clocks, A, B, and C, and they diverge because the clocks, well, they're fairly precise, but not 100%. So they will come to a different value, and these processors want to communicate and reach a common understanding of a single value. So the basic concept is this median clock method. Each processor sends its own value to the other computers. A sends out 10, B sends out 20, C sends out 3. Good. They all have an understanding of the state of the system. Their clock's values are 3, 10, and 20. The median value is 10. Everybody's happy. Now we agree on 10 from now on. The problem is, okay, what if a computer fails? Well, maybe it's not so bad. If it just, doesn't answer, the other ones will just decide. But what if it actually sends different values? Now what? Well, you see, now the state of affairs are understood differently. A now thinks that it has the median value of 10, and B thinks that its value is the median. And now we have chaos, because once we have distributed computer, anybody if they're not working on the same premises, if they don't have the same understanding of the situation, they will not be able to cooperate to solve any problems. So what's the workaround here? Turns out, in this case, you can actually make do with 4 machines, four clocks. So suppose A, B, and D are good, and C is the one who's faulty. You do as before. Everybody sends out their own value. Doesn't matter what, so A has 10, B has 20, and D has 15. Fine. So their partial understanding will be that, okay, they all know that the values are 10, 20, and 15. But what about C? Well, if C sends out the same value to everybody, they all have shared understanding. Fine. What if he sends out different values? Say he sends 25 to A and only 3 to B and D. Well, now they just take the the thing is that they will not only send their own value, they will send out the value they heard C tell them. So A tells the B and D that I heard 25. And B sends out to both A and D, I heard 3. The same with D. Okay? And now A will say here, think, okay, I heard 25, but B and D heard 3. Take the majority of that, that's 3. So we all come to the understanding that the value is actually 3. You see, B, for instance, doesn't know, it will hear 3 from C, it will hear 3 from D, it will hear 25 from A, which must suggest that A is broken, but it could be that C is broken. But it doesn't matter which one is broken. One of them is broken, but now they have a shared understanding. The ones that are correct, they have a common understanding. The faulty one may do whatever, may not understand anything what's going on, but the ones that are non-faulty will have a shared understanding of the state of the system. What if he sends out all different values? 25, 3, and 40. Well, that's not a problem, because now when they receive those values, they will actually notice that there are 3 different values. None of them is the majority, so therefore none of them is valid. So they all put middle, invalid. They all agree. And this was the key idea. Now, Lamport actually, one of his roles was actually to put this into an interesting story. And he called these faults Byzantine faults. Now, what is Byzantine? Well, the Byzantine Empire was what is also called the East Roman Empire. It was the mostly Greek-speaking part of the eastern half of the Roman Empire. This was in the Middle Ages until about 1450, I think. And it was very powerful, and for our time being, for instance, it ruled over all of the Mediterranean. But there was a lot of things going on, and particularly is known for frequent treachery at the high levels of administration. And Lamport put this up into the story. Think about the situation that we have 3 generals. There's one commander and then his 2 lieutenants. And well, they're encircling this enemy that they want to attack. Well, they need to decide whether to attack or not. But if they attack, they better attack together. If one of them attacks and the other ones don't, they're in trouble. But also, if it's the right opportunity and they don't attack, they're also in trouble. Okay, fine. So you have the commander. He sends out an attack message, attack. And since they know that there's some treachery, they're not sure whether he is reliable. So they will actually ask each other, what did he tell you, right? And so if you said attack, okay, we agree, fine. And now, what if it sent retreat? Well, then you hear retreat from the other guys, and you know that he's wrong. That the commander was faulty. Except, do you really know that? Because it could be the case that he actually said attack, but it was the other lieutenant who's faulty, and he then changed it to a retreat. So, which means that you don't really know which one is the faulty one and which is the right decision to make. And you don't know whether to jump or not to jump. So you can't resolve it this way. Their fundamental result was that if you have one trader, then you have to have 4 generals, but it's also sufficient. If you have more traders, if you have T traders, then it's sufficient and necessary to have 3 times T plus 1 generals. Surprisingly clean and amazingly general also. Now, his other contribution was that actually you can do with fewer generals if you can trust the messages. That is to say, the problem was that along the way the message could be changed. But if you have it to be, stamped and signed, well, if you can use digital signature, then you can use actually fewer. It's enough to have simple majority. And this was only some 3 years after the invention of of digital signatures. So the point is that when this guy tells you he's at retreat, he can actually show you the signature, and you can verify that that's actually what the commander says, and therefore you know that the commander was wrong. Now, this was the original paper, appeared in the Journal of the ACM in 1980 with these three authors. A couple of interesting things about it. One is that this is 2 years before I even entered my bachelor degree. This is like decades before I knew that there was something called distributed computing. This was 2 years before the main conference on distributed computing, the principles of distributed computing, or PODC, was even set up. So this is extremely early, which perhaps explains why, if you look at the references, you find all of four references. Of these four, 2 of them are about digital signatures, Diffie-Hellman and RSA. That leaves 2 about the main topic. Well, 1 of the 2 was their previous paper on that particular project. That leaves 1 really related reference. That's how standalone this research was in the day. Now, 2 years later, it actually appeared as in a separate, another paper under this name, Byzantine Generals Problem. There, you also had just 4 references. The 2 digital signatures references, their previous paper from 1980, and a follow-up paper. So there's really no preceding reference being given to the work here. Now, why all this Byzantine stuff? Well, it turns out that he thought that Dijkstra had been very successful with this dining philosopher problem. He thought it was a rather not very interesting problem per se, but he made it really popular so people remembered as a result. So he thought the way to popularize it was actually to present it in terms of a story. And that's why he thought of this. And at the time being, there was a problem in distributed computing, something called the Chinese generals problem. So apparently 2 generals have to decide whether to attack or not, and they're not sure if the message goes through or not, so how can they actually make the decision? Well, he basically stole this idea of the generals. He wanted to call it something else. And, well, he didn't want to offend anybody, so he didn't want to call it a nationality that people would get offended. He actually was going to call it the Albanian generals problem, because at the time, Albania was completely closed society, so he thought that would be pretty safe. But somebody did point out that maybe there are some Albanians living outside of Albania, and maybe Albania will not be closed forever, so it's better to change it. And Byzantine is pretty safe because there aren't many Byzantines around. And anyway, the Turks took over, and so it's no longer even Christian, so it's pretty safe. But the main reason for writing the second paper was to assign the new name to the problem. Well, okay, you needed some new results. Yeah, so he did actually simplify some proofs. He considered some extensions, some practical implications, etc. But that was a pretty successful project, because if you look at the citation in Google Scholar, you find that it's cited 3,681 times. Quite a successful follow-up paper. Now, I was actually at the conference where he was given the award. Here's the award ceremony. It's a very beautiful affair with a concert and nice attire and royalties. And here's the Swedish king giving the award. Oh no, this is not. This is the Nobel Prize. Sorry. The Turing Award is a little bit simpler. It was actually given at this conference in the ordinary hall, simpler than this one, basically. And this is actually my photo taken from the audience. And if you look closely, you can see he's wearing a T-shirt. But even better photo is my colleague, two stories up, because here I am thinking, wow, this is cool. And there he is wearing shorts. So computer science is not exactly like physics and chemistry, right? Quite a bit more informal. Now, I said that he made many contributions, and I will not go into all of them. I should mention this one because it's one of the most highly cited papers in the literature of computer science, called Time Clocks and the Ordering of Events in a Distributed Systems. What's the point there? His point was perhaps the first one to make the point explicit that thinking of time as being a global concept that everybody had the same sense of, it does not really make sense for a distributed system. For one thing, you don't want a master clock that everybody follows because that breaks fault tolerance. You also don't want, well, you could try to have some clocks, but the clocks will drift apart. And this is actually amplified in distributed system by communication delays, which can be sometimes quite arbitrary. So instead, what you want to do is to preserve the things that really matter. Causality is what has to come before another thing. That is causality. If A sends a message to B, then the receipt of the message is clearly later than the sending of the message, right? If A first executed a statement S and then statement T, well, S comes before T, fine. But the other things may occur simultaneously or before or after, or may not matter at all. So what you have really is a partial order. You can turn this partial order into a total order by, say, giving priority to certain computers over other computers. But his point was that instead what we should use are logical clocks. Clocks that don't really necessarily mean seconds, but are basically like a combinatorial entities that increase in the right systematic order. And these are now called Lamport clocks or Lamport timestamps. And it's interesting to relate this to that apparently his reason to go back to grad school was that when he started reading up on physics and found the concept of special relativity very interesting and wanted to understand better the role of time in this time-space continuum. So to him it was clearly natural that not everybody has the same sense of time. Well, the laudatio for the award lists actually many things. First, it talks about foundations of concurrent programming. By concurrency, we mean things that are operating at the same time, possibly within the same computer. And the first thing was so-called bakery algorithm. It is the way of solving the mutual exclusion problem. Mutual exclusion problem is suppose that there's a tool that everybody wants to borrow or use. And mutual exclusion is basically a way of enforcing that if I am using it, you will not come and grab it from me. That as long as I'm borrowing it, I can keep it until I'm ready to give it up. And so that you can trust what you actually have. Now, there was an original solution by Dijkstra who introduced this problem in the 60s, an improvement by Knuth, but Lamport was actually the first one to give a specific feature of it where the writes and the reads are not assumed to be atomic, all happened at the same time. Loop freedom, that also relates to the mutual exclusion problem. Usually you think of it in such a way that, okay, you have everybody standing around this gadget, and they take turns basically borrowing the hammer, right? So first person 1, then person 2, person 3, person 4. But what if, you know, they take different amount of time? What if they're not even there yet when you actually have to want to borrow it? Do you have to wait for the guy who's not even in the bakery in order to get to the cashier? It doesn't make sense. That's what loop freedom is. That you're not slowed down by the slow processors. Sequential consistency means, think of multi-core systems, which are now common today. Okay, so they have some cache memory. The cache is actually can be distributed, but it's supposed to be distributed. Still, it's supposed to be shared by all of them. So it means that the multiple copies, well, they have to be consistent, and he defined the notion of sequential consistency, meaning that it will occur just as if there was a single processor accessing it sequentially. That's his definition. And he was the first one to introduce this. Similar notion is that of an atomic and regular registers. And then distributed programming is sort of like a concurrent, but except that you now have the issue of latency. You have to actually send messages between the nodes, and they can be physically different places with these delays. These logical clocks was a fundamental one, and from that they wrote a paper on distributed snapshots. Namely, you want to get a global snapshot of the state of the whole computing system. Now, once you have these logical clocks, it turns out to be fairly straightforward, but that paper actually received no fewer than 4 different awards, the snapshots paper. Fault tolerance, we've already talked about Byzantine agreements. The concept of state machine replication is the concept of basically how Facebook basically makes multiple copies of web servers that are essentially doing the same thing. Think of them as state machines that function the same way. And then he's also especially in more recent years, worked a lot on formal specification verification of programs, popular topic here. He received the LIX Test of Time Award for a paper with Abadi. He has introduced a formal modeling language and verification tool, so-called TLA, or Temporal Logic of Actions. And this story of Paxos is interesting, actually. So at the time being, he was working for the Digital Equipment Corporation. At the time, for a while at least, it was the #2 computer maker in the world. It later became Compaq, which I think merged into Yahoo, I believe. Or was it the Hewlett-Packard? I forgot. Hewlett-Packard, yeah. So they were building a distributed file system. They wanted certain properties. And he thought, this is impossible. So I set about trying to prove that it could not be done, and I failed by discovering the algorithm. Beautiful. Now that algorithm has been widely used, but then again he thought, well, I have to make it into an interesting story. So I invented the story of the part-time parliament on the fictional island of Paxos, how they come to a decision of since they are not always working in the parliament, they need to actually decide when to meet and make decisions and so on and so on. Well, it was an interesting idea, but as he calls it, it was a complete disaster because nobody could actually understand the story. It actually delayed the paper 9 years. It appeared 9 years after its original tech report. And he says, if it wasn't for Butler Lampson, who understands its practical significance, the paper would have died without anybody noticing it. Exactly, yes. So it required a smart person to understand. Well, this thing is something you see in the real world. Google has a distributed file system called Chubby. Apache has one, and it's been used by Microsoft and Yahoo. And in fact, the concept of Byzantine agreement is actually a key concept in the Bitcoin production. Now, one of the contributions that you might be familiar with is LaTeX, or LaTeX. And the way he writes it is that in the early 80s, he was thinking of writing the book about concurrency. So since he was using TeX at the time, he wrote some macros that he clearly would need. And, well, he thought that with a little extra effort, he could make these macros usable by others. The little effort took about 11 months, but it did result in a product. And this quote by his editor was interesting, which said that, fortunately, I did not listen to your doubt that anyone would buy the LaTeX manual, because more than a few 100,000 people actually did. The exact number, of course, cannot accurately be determined, in as much as many people, not all friends and relatives, bought the book more than once, so heavily was it used. Yeah, mine is probably more used than almost any other book that I have. Meanwhile, I still haven't written the great American concurrency book. I built the tools, but I haven't actually built the road. Now, this one I did not know. So LaTeX actually was a multiple pun. Well, clearly, well, tau came from Knuth, tau, epsilon, chi. That was his great thing. And lay or lies as in Lamport. But lies also as in the, you know, la bella vita, for instance, la bohème. So it's the tech, right? That is also could be understood as LaTeX, which actually as in latex, as in rubber, which also has some kinky notations if you're into that. And he points out that he's much better known as the author of LaTeX than for his real work. People are surprised that I'm not devoting my life to it. Some mention of awards. Maybe the most interesting is that he's receiving, it's piling up in the last 2 years. He's received these 6 awards just in 2013 and 2014. 3 of them on that distributed snapshots paper that I mentioned. And then there are additional awards for the Paxos paper, Byzantine paper, the clocks paper. He has 5 different honorary doctorates, some John von Neumann Medal of IEEE. I actually got stuck because I looked up John von Neumann Medal and I found two other John von Neumann medals by different organizations. So this one is apparently on, well, computing, US Academy of Sciences. I thought it was actually appropriate to play this video. So for the last 10 years or so, he's been working at the Microsoft Research, and they produced this nice video. I hope we can play it.
The Turing Award is for making lasting contributions to the theory and practice of computer science, and Leslie certainly has.
Leslie invented the theoretical foundation underneath distributed systems technology. So the internet is a distributed system. So you like using the internet, you owe Leslie.
Every time you access a modern computer today, whether it's your desktop or even your cell phone over a network, I can guarantee you you're using one of Lamport's ideas.
It's unbelievable what kind of reach Leslie has had on the entire world.
Nowadays, when we have machines with dozens of cores and data centers with hundreds of thousands of computers in them, this is just the way computing's done. And Leslie showed us how to do it reliably.
Anyone who uses the internet, which is an awful lot of people, is depending on distributed systems. Those systems work because of Leslie.
Anyone who has been a student in computer science has been touched by Leslie, because if you've taken an operating systems course, you've probably studied the bakery algorithm, and that's Leslie's algorithm.
It's so simple when Leslie describes it that you cannot imagine how you didn't think of it yourself, which is simultaneously wonderful and extremely frustrating.
Leslie is very unique in the sense that he can really prove to you mathematically the solution is correct, and yet it can be applied to very practical problems.
The algorithms that he designed, which in many cases were not viewed as important at the time, are now fundamental to the way we build web-scale systems, the systems that all of us use every day.
What Leslie's done with this language, the TLA plus modeling language, is to make that accessible to everyday engineers.
His work on distributed systems predated the rise of the internet as a force in the world by many years.
At Bing, we actually really studied his paper on Paxos and applied the technology to build the distributed systems that we still use today.
I've gone back and read recently some of his papers, and I still have not been able to exactly get inside his head and figure out what he was thinking when he came up with it.
What he did want to do is build something solid that people could count on for 40 years, 100 years, whatever else. I mean, what he's got, you know, is a mathematical truth, just as much true as 2 + 2 = 4.
I can't think of any single person who's had a more profound impact on how we think about concurrent systems and making concurrent tasks perform correctly.
What Leslie has taught us, probably more than anything else, is the importance of keeping the mathematical principles, the mathematical underpinnings of computing firmly in mind when you build systems.
He can take and analyze problems and construct mathematical proofs like few people in the world can. Maybe 5, maybe 10, I don't know. Not many. I can't. Most people can't.
Without Leslie's innovations, which in many cases were not appreciated in an instant, we wouldn't have the computing environment that we have today.
Leslie, congratulations on winning the ACM Turing Award. Microsoft is extremely proud to have you among us.
The rest of it is celebration.
Congratulations.
So that gives you perhaps some idea of of how people see it. And Microsoft is clearly proud of having him on his staff. Now, I thought it would be cute to actually look at well, his papers, and he has some description of what was going on when he was writing it and how it actually went. And interesting to see actually the difficulties people run into when trying to publish it. And you run into a number of things. For instance, this paper, which he said is submitted to a conference held in France, the thing at the time. I was told that my paper was rejected because they accepted a paper by Noelle on temporal logic, and they didn't feel that such an obscure topic merited 2 papers. I then submitted the paper to Fox, where it was also rejected. I have very rarely resubmitted a paper that has been rejected. Fortunately, I felt that this paper should be published. It has become one of the most frequently cited papers in the temporal logic literature, 500 citations. This happens to the big guys also. Here's another one which stayed unpublished. This is a totally revised version of 9, complete with proofs, which had been admitted there. I submitted to CACM, but the editor of CACM decided it was more appropriate for JACM. When I submitted there, the editor rejected it without sending it out for review because the basic ideas had already appeared in the conference version. By the time I realized how crazy the editor's decision had been, it didn't seem worth the effort of resubmitting the paper. Here, the referee said of the initial submission that the proofs were too long, tediously proving the obvious. In fact, there was a bug in the initial version, and at least one of those obvious proofs was of a false statement. Needless to say, I corrected the algorithm and wrote more careful proofs. And he's actually known for giving very thorough proofs, so that might be a reason why people find them long and tedious. Here's a paper that did appear. The formula seems to have been almost completely ignored, even among the theoretical concurrency community. I find this ironic. There's a field of research known by the pretentious name of true concurrency. My formalism is the only one I know that could therefore be considered truly concurrent, which he argued. But as far as I know, the true concurrency community has paid no attention to it. So, in the end, so I'm done early, almost done. You might ask, so okay, so why did it appear that, why could he solve these problems? Why did he come up with the problem? How could he come up with the solutions? His answer is that when I look back on my work, most of it seemed like dumb luck. I happened to be looking at the right problem at the right time, having the right background. Luck favors the prepared mind, as it says. And I think it's also the case of how you look at it. The way I read it is that his story of that when you look at an interesting practical problem, you strip it down to some bare fundamentals, and then you apply an innate guide to solving it, not because it's so the popular technology at the time. You solve it really rigorously, and you make sure that it holds for as general cases as possible. Just because you solved it for your system, that doesn't mean that you should only describe it for your own system. You should think of the global repercussions. And I wanted to end on his most famous quote about what a distributed system is. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. Thank you.
Magnus, we actually do have time for questions. So, well, I have a question. So, do you have any idea why you wanted to write the great American concurrency book?
No, I don't know. I don't know if it was supposed to be particularly American in nature, or I took it just to mean that it was, you know, like a somehow statement of something being of somehow greatness in general.
I know that Byzantine Empire has gone on record as calling some of the European research on concurrency theory has only been able to prove the correctness of biscuit machines.
Of what? Biscuit?
Biscuit machines.
Okay.
So, I think somewhere there's still a record of discussions. He had, I think we're talking about the late 80s when I was a PhD student, where he was discussing on the concurrency mailing list with other people, including other Americans like Montrat, on good formalisms for discussing concurrency theory. And those make for very interesting reading, actually. So
I can imagine.
I'm trying to dig up the link.
Yeah. Well, you can tell actually from his writing. And also, I could see from his demeanor at the conference, he's not really the comedian type, right? It doesn't laugh very much, and he seems he has strong beliefs that he's not afraid of voicing. So I'm sure it's what do you call it? Not everybody's cup of tea, perhaps.
We heard the video from Microsoft Research where everybody was praising Lamport's work. So how much of your work, for instance, is influenced by Lamport, since you're working in the computing community amongst us?
Yeah, I have to admit that, well, one reason why I wanted to give this talk was to actually learn this stuff. Because what I have been doing has not revolved around this topic at all. I've only worked with basically synchronized algorithms, in which case, and without any kind of much of a fault tolerance, I would say. So, in which case these issues are, moot.
Yeah. Do you know anything about lineage, like other? I mean, Hasan actually has a PhD student, so he's looking in this research settings.
Right. Yeah. So he's been at Research Institute all his life. Yes. All this time. So he started at this Compass, then SRI, then at DEC Systems, and I think maybe there was something in between, and then he went to Microsoft. So I don't recall anybody who was supposed to have been a student. No. Right. Yeah. I mean, yeah. I didn't see many papers with junior people either, although there must have been some also.
Okay, so if there are no further questions, Magnus can answer questions offline, and let's thank you. A great start of season 4 of Personal Computation.